Hi, this is Joseph Gugliardi, and you are listening to my Monte Carlo 4 homework, or lab 4 for Monte Carlo, and this was an optimization lab. So as you can see, this is my pseudocode for this problem. First, I initialized some variables. So the first problem was essentially, let's pull it up here. First problem was to minimize this z equation given a couple constraints for x1 and x2, so a two-variable equation that we wanted to minimize. So in order to do this, we had to initialize some variables. X1 as the first random normal coordinate value, and x2 is the second random normal coordinate value, because we're going to be doing Monte Carlo for this. We got temperature, we got iterations, sigma, a counter, and the current best is infinity, because we're just going to go down from there since it's minimization. So the result is to minimize the equation's output for best set of inputs x1 and x2. So here we have the equation laid out here that we want to minimize. So running through this code, pseudocode rather, for each iteration 2 to n, because we've already defined the first iteration, there's a loop. And x1 is defined as the minimum of 5 and the maximum of 0 and the random normal of the previous iteration of x1, given also sigma. And x2 is the minimum of 5 and the maximum of 0 and the random normal of the previous iteration. So then we have an if statement here. So if for the current iteration 2x1 plus x2 is greater than or equal to 10, and x1 plus x2 is greater than or equal to 10, then we have some things that are going to go on here. So this covers two of our constraints right there. The candidate for z is set to z x1, a function of z x1 and x2 for the current iteration. And then the current z is set to z x1 and x2 for the previous iteration. So this is where the comparison is going to happen. So then if, the second if statement, exponential of negative z current minus z candidate over temperature is greater than or equal to a random number, then the current z is set to z x1, x2 for the current iteration. This is where, if this is the case, this is where the brains is happening here of the algorithm deciding to move or not to move to the next, taking the candidate as the current, moving to the next location. Else, if it's not, this is particular for minimization, x1 of the current iteration equals x2 of the previous iteration, x2 of the current iteration equals x2 of the previous iteration. There's a reset that happens here, and then that's the end of the second if. And then the third if z candidate of the current iteration is greater than the best of all iterations, then the best of all iterations equals the z candidate. And you increment this counter by 1 because you want to record how many times it found a new candidate and display the best x1 and x2 in a counter by 2, whatever counter ends up being, by 2 matrix. And the third if, else you do nothing and you end the first if. Here, before you go back to end the for loop, you want to reduce the temperature by a factor of 0.95, multiply it by 0.95, and you end your for loop. And you'll run this for as many iterations as you have. So I have the code here for the first problem, and I didn't write out the pseudocode for the second problem because it's very similar. The only difference with the second problem would be that the equation, the z equation that you would be using would differ. So if you can see, is in problem 2, I have a function equation here, and I have defined my z, which is different here, and the constraints are slightly different as I have shown here. So in conclusion, Monte Carlo can be used in optimization to maximize or minimize an equation given one or more multiple variables that are based on random variates. This, combined with simulating annealing and an acceptance criteria, moves the algorithm from a greedy algorithm and into a random search algorithm. Lastly, the third problem was a TSP problem using genetic algorithm. So our goal here was to minimize the route distance to find the shortest path that the salesman will travel to all 10 stops using this genetic algorithm. So we have the number of stops. XY is 10 random coordinate locations of stops. The DMAT is a 10 by 10 matrix of distances from stop to stop. Population is the population matrix of random routes. P is the size of the population, and best route is the current best route distance initialized as infinity. So we have the calculation output of results. So here we're creating that matrix of distances, and we have also created a population matrix of the random permutations. Then we have our for loop for 1 to 10,000. This is creating that population, or for each, sorry, the population was already created. This is for each permutation within the populations. The population permutation of the current iteration is set as the route. The route must circle back to the first stop. The cost of the route of this current iteration is a function of route DMAT, and which is the route itself, the distance, and the 10 stops. How many stops there are, which is 10. So here I've just defined this function as you would need it in whatever software or whatever you're going to need. You want to initialize the distance as 0, and for each iteration, 1 to the number of stops minus 1. Distance is equal to itself plus the distance matrix value of the route at the current iteration and the route at the current iteration plus 1 from one stop to the next stop. And if cost of route, then we're getting into more of the algorithm here, of the route at the current iteration is less than the best cost, then the best cost is set equal to the route at the current iteration. The best route is equal to the route permutation of the current iteration. And this is where the genetic algorithm is happening. A random number is set to a random integer from 1 to n. A random number, which is number of stops, and random number 2 is also set here. And so we can do a swap here, replace the first row of the population permutation with the current iteration of the population permutation, and mutate the first row of the population matrix by switching stops R1 and R2 in the population permutation. This means you take R1 and R2 wherever those are in the array, and you switch those stops. And that's going to end that if statement for the mutation, and you'll end the for loop, and you'll continue this on. So I have the code for that. And yes, so genetic algorithms can be used to optimization to minimize or maximize a route. So now let us go to the code real quick and watch this happen. So here's the first problem. We run this section. We will see that the best route is 176.6276, and the best x values are 2.5 and 5 for x1 and x2. Then we go to we have the second one below, which we can run as well. Second minimization problem. And for this one, you'll see this down here because I actually defined my own function for this one in a separate file. And once that's finished running, we will have the value here. So it minimized and got a very small value of -3.79 times 10 to the 6th, which is pretty low. It's pretty small. And then lastly, we have our genetic algorithm, which we will run. When we run that, we will actually get the route itself, and the distance was 2.46. As you can see, this genetic algorithm could be greatly improved. There's a lot of crossover, a lot of distances here, by using different mutations and such. So this was my Lab 4. Thank you for watching.